So, in this lecture we will see polarization of an antenna. Now, polarization is actually in antenna, if it is a radiating antenna or transmitting antenna, polarization has one meaning. If it is a receiving antenna, polarization has a slightly different meaning. Now, please remember that polarization of an antenna means that one thing is polarization is different in different directions. So, when we say polarization of an antenna, we should also specify in which direction polarization we are talking of. Just the concept of directivity, gain, etc., that generally we say an antenna has so much directivity and antenna has so much gain, but it is with respect to certain angle or certain direction, solid angle, that means theta phi direction. Similarly, polarization is also that polarization of an antenna in a given direction is defined as the polarization of the radiated wave when the antenna is excited. That means, whatever wave it is radiating, the polarization is for that. So, to understand antenna's polarization, we need to understand what do we mean by polarization of a wave. That means, an electromagnetic wave, what is the polarization is this. What is the definition of polarization of that? Now, before going there, I now want to say that what is the reverse case, that means, if the antenna is receiving antenna, what is the meaning of polarization of the antenna? So, in that case, it is the polarization of the incident wave or incoming wave to the antenna from a given direction, which results in maximum available power at the antenna terminals. What do I mean by that? So, this is a receiving case. That means, I have a receiving antenna. So, this is my antenna, the wave is coming. So, I am saying okay, from this direction I want to see. So, this wave, what is its polarization, provided I get maximum power, maximum available power here. So, if not, then there will be a mismatch, there will be a loss, etc. Now, as I said, if the direction is not stated, because many times you will see that okay, it is a so and so polarized antenna, that means he is not specifying theta phi. In that case, the direction is taken to be the direction of the maximum gain. So, antenna's maximum gain, that has a direction, because gain is a theta phi function. So, gain without theta phi means in a maximum of that function. So, in that direction the polarization is talked when nothing is specified. Now, then let me recall what is the polarization of an wave, electromagnetic wave. Actually, it was taught in electromagnetic theory. So, it is that property of a radiated electromagnetic wave which describes the time varying direction and relative magnitude of the electric field vector of the wave. So, what is the polarization of an electromagnetic wave? It is the time varying direction and relative magnitude of the electric field vector. Basically, in mathematical terms, we can say the locus of the electric field vector with time. So, it is basically the locus of the end point of the electric field vector at a fixed location in space, and the sense in which that locus is traced as observed along the direction of propagation. Now, these are actually exact terms, but to understand that, let me draw a plane wave. Okay. Suppose a plane wave, generally what we say that the plane wave electric field vector is something like this. So, this is the envelope of the electric field vector, envelope of E field. So, obviously that means this is a, you see, spatial description of the wave. That means at a particular time I am seeing that at this point electric vector is like this, at this point electric vector is like this, etc., etc. Okay. Now, instead if I take a, if I fix a point and go on see that what is the polarization or what is the electric field vector as time progresses. You see, I will get a picture like this. You see, suppose any point you fix. So, here if I fix, I think you will agree that I will get, suppose I am at this point, I am here. So, I will see something here. Next moment it will rise a bit, then it will again be like this, then it will 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 be like this, then after that again it will be like this, like this. You see, this is for a plane wave. Obviously, I have drawn a plane wave, but instead of drawing it, generally we always draw the thing as a spatial variation. But if we see time variation, this electric field vector, its end, how it traces, what it is tracing? It is tracing a line. So, it is a linear polarization. Now, instead of this, this also is a linear polarization case. You see, it need not be always like this vertical or horizontal, it can be something like this. This is also a case of linear polarization. This is also a case of linear polarization. But linear polarization again is a special case. Actually, all things need not be linear. So, polarization, it basically most generally it should be classified as elliptical. Why? Because this E field vector in general that can be broken, because you see wave is propagating in a direction, the E field that is can have a two dimensional representation. So, usually we represent it with x and y. So, in general this electric field vector will be having an x component and also a y component. So, in general the locus that it will trace as the time progresses, if I stay at a particular point and see the electric field vector at that point, over time I will see that the tip of that electric field vector is tracing an ellipse. Special cases of that, Sometimes this ellipse becomes a circle, that time we call it a circular polarization. Sometimes that ellipse becomes a line, that time we call it a linear polarization. Now, the E field vector, when it traces an ellipse, what is an ellipse? This is an ellipse. Now, as time progresses, the electric field vector tip, suppose this is the tip of electric field vector. These are all electric field vector with time. So, you see in this case, it is tracing an ellipse in a clockwise direction. I can also have a case where so this is a ellipse. So, that means I will show that this is a clockwise, this is an anti-clockwise. So, this gives us the sense. So, this one is called CW, clockwise sense, this is called CCW, counterclockwise sense. Now, sometimes the CW is called right hand polarization, right hand polarized wave, and CCW is left hand polarized wave. For obvious reasons, you see that CW means right hand and this CW is left hand. This is a nomenclature, but the more important is this clockwise, counterclockwise. Now, what we require for our things is, as I was saying, that most general description of an instantaneous E field will be something we know that if anything is a field, it should have, I mean a field and wave, it should have a time function as well as a space function. So, E j t, so this can be, if I say that I will have x and y component, any two dimensional component. So, I can, the instantaneous E field of a plane wave travelling in a, please remember this discussion is travelling in a minus z direction, can be written as E x z t a x plus E y z t a y. In the Cartesian coordinates, a x, y are unit vectors, and E x is the amplitude of the x component of the field, E y is the amplitude of the y component of the field, and time phase of this E x component, or I will write it like this because there are also the time phase. Let us also say that, so I will write like this, the amplitude of E x is E x, amplitude of E y is E y, time phase of E x is phi x, time phase of E y is phi y. So, can I write what is this phasor Ex? It is the real part of Ex e to the power j kz, because it is a wave going into minus z direction, minus j kz plus phi x e to the power j omega t. And what is the Ey phasor? It is real Ey e to the power j kz plus phi y e to the power j omega t. So, I can just write Ex is nothing but Ex cos kz plus cos omega t plus kz plus phi x, and dy is Ey cos omega t plus kz plus phi y. Now, for the wave to be linear polarized, what I demand? The time phase difference between the two components must be an integral multiple of pi. That means, what I want is del phi, which is nothing but phi y minus phi x, that should be n pi. N is integer. This is called linear polarization. For circular polarization, what I demand? That Ex magnitude and Ey magnitude to be same. Also, I want time phase difference is odd multiples of pi by 2. So, that means, this means I want phi x phi y minus phi x is equal to 2n plus 1 pi by 2 2n plus 2n odd multiples of pi by 2. So, I can write 2n plus half into pi, n is equal to 0, 1, 2, etc. for CW, and minus 2n plus half pi, n is equal to 0, 1, 2, etc. for CCW. Okay. You can simply do it. Actually, in class 12, some of you may have done it. And please remember that if the wave propagation direction is reversed, that is, instead of wave propagation in minus z direction, if I have z direction, then these two will be opposite. That means, this will be CW, this will be CCW. So, for circular polarization, the important thing is magnitude of the two components should be same, and time phase, the time phase difference between the two components should be odd multiples of pi by 2. So, this is the demand for circular polarization. And what is elliptical polarization? So, elliptical polarization means that magnitude wise I don't require any relationship. So, Ex magnitude and Ey magnitude, no relation. And time phase difference, so delta phi, it may be odd multiples of pi by 2 or not odd multiples of pi by 2. That means, here also no difference. That means, this was the most general case. Now, that if it becomes odd multiples and these two are equal, that becomes circular. If the time phase difference become that odd multiple of a integral multiple of pi, or you can say even multiple of pi by 2, then it is a linear, etc. So, ultimately we can say that if this is our actual rectangular direction, but the ellipse may be having a tilt. So, this ellipse, obviously, if this is larger, this is called major axis of the ellipse, that means here to here, and here to here it is called the minor axis of the ellipse. Now, this how much is this 2? Actually, you know that this 2 means what is the maximum of the Ex component and what is the maximum of the Ey component. That ratio is an important characteristic thing of the polarization of the wave. That ratio is called axial ratio, AR, that is given as major axis by minor axis. So, if we say that this is O and this is A and this is, let us say, B. So, I can say it is OA by OB, and generally this axial ratio will vary from 1 to infinity. Okay. So, this is the polarization of the wave. If we understand that, then we can understand that if for a transmitting wave, it will be the antenna's polarization, that means the antenna is radiating a wave. So, in general the antenna will have elliptical polarization, but if the two radiated waves, the x and y component, they have these relationships, then they may become circular or then they become the. So, now what is polarization loss factor? The polarization of the receiving antenna may not be the same as the polarization of the incident wave. If they are equal, that means whatever the polarization of the incident wave and the antenna's polarization, that means as a transmitting antenna's polarization is same, then this receiving antenna will be able to extract maximum power, otherwise there will be a polarization mismatch. So, let us say that we have a incident wave. So, this is again I am discussing polarization loss factor, already we have seen it in case of efficiency time. So, that suppose I write like this, that A I is the unit vector in the direction of the incident E field, and the polarization of the receiving antenna, that is, let us say EA. So, what is the unit vector A antenna? A antenna is a unit vector in the direction of the antenna polarization. Then what will be PLF? PLF will be simply the magnitude of these two directions dot product antenna. You can say this square. So, if we draw that this is the AI vector and this is the A antenna vector, then and this angle is phi p. So, I can write this is cos phi p square. This is also a dimensionless quantity, cos phi p. So, that means these two angles. So, by that, so now we can ask that if the antenna is polarization matched, what will be the value of PLF? That means, in that case this angle will be 0. So, cos 0 is 1. So, we can say that matched case PLF is 1, and fully mismatched case, that means orthogonal case, PLF will be 0. So, what I can say? So, orthogonal PLF will be 0. Sometimes people say PLF dB. So, is log of this PLF. Now, here multiplier I will have to use 10 or 20. It is all power thing, that is why it is 10 log 10. Now, this polarization loss factor is important for link budget calculations in space communication, radio astronomy, etc., because this, since they are having a very tough budget. So, this factor, some cos theta thing, that is important for them. So, that is why this also should be taken into account. Now, so we have seen in detail what is the polarization of the antenna, because a designer should be knowing what is exactly mean by polarization. Then we will see that sometimes in the actually antenna is its design, etc., is completely different from any other element that is in the whole link, but when antenna should always be either connected to the transmitter or to the receiver. Now, from if you look from the transmitter or look from the receiver, antenna is nothing but it should be characterized by an block who is doing something, he is radiating, etc., but to a transmitter it is taking some power and it is developing something. So, that means anything in electronics, any two port network, we characterize it by an impedance. We do not characterize it with voltage or do not characterize it by current, because those are our excitation and effects, etc., but the characteristic of the block, that is the ratio of this voltage by current, that is the impedance, because that does not change. Whatever voltage I give, whatever current I give, as long as that impedance is within the range of its validity, the impedance uniquely characterizes the two port network. So, antenna also, when a transmitter is looking at antenna, it should be characterized by an impedance. It may be a radiating device, but it is taking power. So, that time it should be behaving as an impedance. Similarly, when it is receiving, it is taking the power, but finally it is delivering it to a load. That load may be a spectrum analyzer, that load may be simply a resistor, that load may be simply an inductor, anything. So, that time it should also be described by a impedance. So, that means ultimately here you see, when we analyze the antenna, it is a completely field theory concept. We have seen in case of current element how we solved Maxwell's equations to find out what is the EH, etc. But then from there you have seen that we were able to find out how much power, etc. it was giving, and ultimately we could see that okay, a current element, what is its radiation resistance. That means we again could relate that field theory thing to a lower level theory called circuit theory, that it is also a radiation what is taking place, we have modeled it as a resistance. So, now we should be able to model this whole thing. Also we have seen that near the antenna there is a field which is not propagating, it is a reactive field. That means it should be characterized by some reactance. So, there are also we have seen that there are losses in the antenna, etc. So, there is a lossy resistance also. So, lossy resistance, a radiating resistance, then a reactance. So, that means it should be characterized by an impedance, that is called input impedance of the antenna. And actually a transmitter looks at the input impedance, because a transmitter knows that he will have to deliver the power. How much power he will deliver to it, how much of that will be used for that calculation, we need to characterize the antenna by its input impedance. Similarly, in the receiver side, ultimately receiver will have to know that I will have to extract power from the receiving antenna. So, what is the impedance of that antenna, receiving antenna, so that I can extract power. So, these are required, and this we will take up in the next class, that what is the input impedance of the antenna, and then we will see a concept which is required for receiving antenna, that is the effective aperture of the antenna, so that we can do all these calculations. So, that means we can now go at our will from field theory to circuit theory, so that we can do the circuit problems, microwave circuit problems. Also we will be able to find out what are the fields radiated by the antenna at any point in the whole universe, what is the field that antenna gives, that will come from field theory, and knowing that field theory values, we will be able to tell what are the impedances, what are the as the transmitter sees, as the receiver sees. Okay, thank you.